Polymers. You may know what they are, or you may not. But I was to tell you that they're just a fancy name for plastics, well, I'm sure you all know what they are. And I'm also pretty sure that what you'll think of is food packaging, or polluted environments, or suffering animals. Plastics aren't the best loved materials at the moment. After all, they're killing our world, right? Well, I'm here to tell you that that's only one side of the story, and to give an example of how polymer chemistry is being used to save lives, not destroy them. Polymers in firefighting. Now, in order to understand what I'm about to tell you, we first need to have a look at what a polymer is. A polymer is a large molecule that consists of lots of monomers linked together. These monomers can be the same, a homopolymer, or they can be different, a copolymer. Okay, so what's a monomer? A monomer is just a small molecule. It can be simple, or it can be complex. It can be aliphatic, or it can be aromatic. It can be organic, or it can be inorganic. The only thing they have in common is that they can be made to form long polymer chains in a process called polymerization. So, how can these polymer molecules be used to fight fires? Let's start with a simple polymer, polyacrylamide. Acrylamide is an example of an alkene as it has a double bond between two carbon atoms. This double bond makes it susceptible to attack from unpaired electron species called radicals, and can therefore undergo a form of chain growth polymerization called free radical polymerization. Radicals are often formed by the splitting of peroxide groups, and can therefore take the role of initiating the reaction. The electrons of the double bond unpair, and one moves to each of the carbon atoms. This initiation process produces another radical species with the unpaired electron on the carbon atom that wasn't attacked by the initiator. From here, the reaction can propagate by attacking another monomer, using the same mechanism and generating longer radical species. This repeats over and over again, forming long polymer chains that are still highly reactive. In order for the reaction to terminate, one of two things must occur. The first possibility is that two of these chains would react together to form a non-radical species that is far less reactive. Alternatively, a less common possibility is that one of the radicals would remove a hydrogen atom from the main chain of the other. This leads to the formation of both an alkane and an alkene by way of a disproportionation reaction. Okay, so we now have polyacrylamide, a collection of long polymer chains. But what if, instead of using pure acrylamide as our starting material, we had also added a small proportion of NN-methylene bisacrylamide? As you can see, this monomer contains not only one, but two alkene groups, and can therefore form part of two different polymer chains. This allows a network of cross-linked polymers to be formed, and is where firefighting properties begin. Within the pores of the cross-linked polymer, water molecules can form hydrogen bonds with the acrylamide monomers. Our polymer now turns from a powder into a gel-like consistency with much more effective cooling properties than pure water, reduced runoff and lower probability of evaporating before contact, making it a much more effective fire retardant and combatter. But scientists still weren't happy with this. They decided to try to maximise this water holding capacity by again adding different monomers to the chain. This time, 2-acrylamido 2-methylpropane sulfonic acid sodium salt was used, a monomer containing almost twice as many possible sites for hydrogen bonding. The result? A hydrogel with an astonishing capacity of over 1,200 grams of water per gram of polymer. This product is now used globally to extinguish forest fires aerially and to protect properties and people. However, To ensure everybody's safety during a fire disaster, not only the victims need to be protected. Polymer chemistry is also vitally important in the protection of firefighters working to extinguish a blaze. Protective clothing allows them to do their job safely and effectively, so let's take a look at which polymers they consist of. The main constituents of fireproof protective clothing are the two polymers, Kevlar and Nomex. As you can see, the structure of these compounds are remarkably similar. They're both examples of aromatic polyamides. This simply means their backbone chains are made from a mixture of aromatic rings and amide links, formed by a series of condensation reactions between monomers. The only difference is the positions at which the chain attaches to each ring. When the two chains are attached to carbon atoms at positions 1 and 4, the compound is referred to as para, such as in Kevlar, whereas when the two chains are attached to the carbon atoms at positions 1 and 3, the compound is referred to as meta, such as in Nomex. For example, in Kevlar, the monomers paraphenylene and paraphenylene dicarbonyl chloride are used for synthesis, whereas in Nomex, both meta compounds are used. In both reactions, one molecule of hydrochloric acid is released for every amide link that is formed. The linear structure and presence of multiple amide groups in Kevlar allows the chains to tightly fit together and form extremely strong hydrogen bonds. Coupled with the rigidity that comes from an aromatic backbone, this makes Kevlar an incredibly strong material that is even bulletproof. Due to the metastructure of Nomex, its fibres are slightly weaker as the molecules cannot line up as perfectly and the hydrogen bonds are not as strong. A mixture of the two fibres therefore makes for a flexible yet strong composite that is perfect for making protective apparel. Both polymers also have inherent flame resistance due to the strength of the bonds that form their backbones, providing the perfect barrier between a flame and a firefighter's skin. It's clear to see that polymers are useful for a lot more than just packaging food and destroying our planet. I hope you've learned a little more about some less commonly known uses for these revolutionary molecules, and the way in which they silently impact the lives of millions of people globally.